I'll try to share my screen. It says host disable participant screen sharing. Can you check that?
Yeah. Donna, is there something we need to do to enable screen sharing?
Okay,
Donna?
that should be good now. Yep.
Great.
Okay. So, is that okay? Can you see a slide?
Yeah, that's great.
Motivation.
Yeah.
That's not actually my first slide is this one. So this is a presentation about mass and velocity and isotope profiles of Go-green clusters. And there is, of course, contribution for all people from Go-green, but most notably Remco and Michael. And what is this about? Why do we want to understand the mass profile and the velocity and isotope profile of clusters, a high redshift? Basically because we expect from theory that cluster mass profile shape change with time due to several physical processes, among which adiabatic contraction, AGM feedback, and accretion of the subclusters, which change the inner slope of the profile or also the outer slope. And the second thing, the velocity and isotope profile, which I call beta of R here, following tradition of Bini and Tremaine. This is related to how the galaxies orbit in the clusters. And this is presumably related to the galaxy evolution, because of course, if galaxy evolve with some relation to the environment changes as the galaxy changes, move along its orbit. And it's important to know whether the galaxy would go very deep near the center, if it is on a radial orbit, or if it avoids the center being on a tangential orbit, because this would change some importance of effects like ramp pressure of tidal stripping. So how do we do that? We have first to identify which are the spectroscopic members. So this is much more delicate than when you're doing this sort of luminosity function analysis, because you want to be very precise on the dynamics. The other thing, we need the statistics. So we have to work on a stack cluster. So we have to find a way to build a stack cluster. And then we're using two methods to determine the mass profile and the velocity and isotope profile. One is called MAMPOS, the other is called Jeans inversion. I'll describe them very, very concisely. And the data set, of course, is Go Green plus G class. There are some very limited amount of literature data added. Okay, so that's the data set I'm using. As you see, there are 5 sparks clusters from G class and 10 sparks and SPT clusters from Go Green. And they're not the entire data set, because as you'll see, what I need is to rather precise estimate of the loss dispersion of each cluster before stacking. So you need some amount of redshifts per cluster as well. And here's distribution in redshift. You can see that, can you see by pointer, by the way?
Yes.
Okay, so you see the distribution in redshift of the sample, going from 0.9 to 1.4, and the distribution in mass is pretty peaked at the value 14.4 in log M200, and that means basically these are massive clusters, okay? Because at that redshift, these are really massive clusters. Okay, the first thing we have to do, we have to define which are the spectroscopic members of these clusters. So we must define a cluster center to start with. In velocity space, it's pretty straightforward. You can identify the peak in the velocity distribution and then iterate and use some robust estimate of the mean of the velocity distribution. In the coordinate space, it might be a bit more subtle, and we investigate in 2 choices so far. One is to use the position of the brighter cluster galaxy. It's not always an obvious choice, but Remco and Jeffrey worked a lot on that, and we think we have the correct VCG. And we're also investigating the alternative of using luminosity weighted centers, but this analysis is still ongoing. So what I'm going to present is based on the VCG centering. Now for the membership, without going too technical, basically we're using three membership methods. One is KMM, which works on the full velocity distribution, and basically it considers mixtures of Gaussians to identify something in velocity space, which might be a subcluster projected along the line of sight, and to remove that from the sample. But then once you identify the main peak in velocity space, you want to refine the identification of members using the projected phase space. That means using the rest frame velocity of a galaxy with respect to its distance from the cluster center. That's why we need the center and the centering velocity. And we're using two methods which both use this projected location in projected phase space, but they are very different conceptually. Basically, one uses models for mass distribution, and the other uses no models, but just a non-parametric approach to the identification of gaps in this projected phase space. This is called clean and clamps, and using two methods, of course, allow you to have a grasp on the systematics of membership. I must say that in the end, the results are very, very consistent between the two methods. But I do assign weights depending on whether a galaxy is identified by both methods as a member, or in that case, I assign a weight of 1, and I assign a weight of 1/2 in the analysis, whether in the case of only one of the two methods identify the galaxy as a member. In total, the two methods identify 677 cluster members in these 15 clusters, although the sum of the membership weights is 613.5. Basically, some members are not identified by both methods. And then once you have the members of each cluster, you want to do the stacking. That's because you want to have statistics to do this game, to play this game, to define in the end, to determine in the end an average mass profile and velocity isotopic profile. So what you do by stacking, following a long tradition, is to use galaxy cluster-centric projected distances and normalize the radii R, normalize this R by the R200 of the cluster to which the galaxies belong. And symmetrically, the rest frame velocity, people have been normalizing that to the velocity dispersion, but it probably makes a bit more sense to normalize that by the circular velocity V200. Although in the end it comes out to be essentially the same kind of normalization, because we do determine R200 from the velocity dispersion. And actually, you might probably know that given the cluster mean redshift and the cosmology, so if you know the cosmological parameters, once you have R200, you also have V200. And once you have the 2, you also have M200, the virial mass of the cluster. So basically, it all comes out to determine R200. And this can be done by several methods in general in clusters. In our case, we have to use kinematics. So we use velocity dispersion, and they use 3 different prescriptions to go from velocity dispersion to R200, scalar relations, basically. And we check that using the 3 different prescriptions doesn't really change the resulting distribution of the stack cluster in projected phase space. We use the cohomology 2D analysis to check for that. So it doesn't really make much difference. And then, of course, we assume spherical symmetry. This is not in general a good assumption for an individual cluster. But Van der Marle has shown 20 years ago that this is actually a good assumption where you stack clusters together, because you don't have a favored orientation in general. Although you might hit trouble if your cluster are, for instance, selected with the main axis along the line of sight, which could be the case in some cluster identification surveys. We assume this is not the case here. Okay, this is the stacked projected phase space of the 600 and 700 members. Big dots are for members with a weight of 1, small dots for members with a weight of 1/2. And the orange lines there just to drive the eye, because these are the escape velocity curves that you would guess for a cluster assuming a typical Navarro-Frenkel white. And so you might see that basically, as you would expect, the membership identification more or less follow the caustic defined by the scale velocity curve. So it's more of a consistency check to draw these lines than anything else. We're not using that for the membership definition. The weighted average of the cluster R200 is 1 megaparsec, 0.98. So this is very convenient because whenever I'm showing things in units of megaparsec of R200, it really makes no difference, okay? It's always 1. Okay, so the Jeans equation, as usual, you want to relate the observables to the mass profile and to velocity isotope profile. And without going too much detail, you know, there is the 3D number density profile here, the velocity dispersion along the radial direction, and this beta, which is defined as the ratio, 1 minus the ratio of the kinetic energy, basically in the tangential direction of the motion and the radial direction of the motion of the galaxy. The fact is that if you're an observer here, you only observe the combined of the projection, the sum of the projection of these two vectors along the line of sight. So this introduces a degeneracy. When you want to determine the mass profile, you should know beta as well, and vice versa. So this is called the mass anisotropy degeneracy, or in jargon is the Jeans madness. So if you want to cure the Jeans madness, you have to do something clever. We think we did this so in 2013 with Gary Mammon and his student Bouet. That was an idea basically to use the full distribution of galaxies in projected phase space as shown here, and assuming models for the mass profile and for beta of R, find out which are the best fit parameters that basically gives the maximum likelihood of observing the sum, all these galaxies, all these members in projected phase space. So what's the probability? The method says what's the probability of observing this galaxy at this velocity at these radial distances, given mass profile and velocity result profile. Okay, this is a panel showing how well Mampost retrieves the true quantities given simulated halos. But more or less, of course, it doesn't cure the Jeans madness completely, but it goes in that direction. And then once you have the mass profile from Mampost, you can get the velocity isotope profile. Well, Mampost in principle gives you both, but it has to assume models for mass profile and velocity isotope profile. And theory is very good in predicting which are the mass profiles of clusters, but doesn't tell you much about the velocity isotope profile. So I prefer to define the derived velocity isotope profile after running Mampost. After running Mampost, I get the mass profile, and then I use the two observables, which are the number density profile here, and the line of sight velocity dispersion profile, which are basically projection of this phase space diagram onto the X and Y axis. This plus this plus this immediately gives you velocity isotope profile. You need some smoothing and interpolation, but in the end, that's direct. So you don't need to assume models for beta of R in the end. Okay, the number density profile can be derived independently of all these by, if you know the correction for incompleteness, and that's thanks for Remco for doing that. And this is the result. This is for all clusters, the BCG center. And it's best fitted with a Navarro-Feinberg wire profile in projection. And this is, gives you concentration for the spatial distribution of galaxies of around 4. Which is pretty normal for a cluster. Then we run Mampost. Once you have, so we run Mampost basically using this information about the spatial distribution, and we run Mampost on the velocity distribution of galaxies, which is dependent on the radial position of the galaxies as well. And I don't need to go in much detail, but we consider a battery of models for the mass profile and for the velocity anisotropy profile. And in the end, we find out that the data, although these are the best data you can get at redshift above 1 for clusters, are not, the statistics is not good enough to tell me to tell us which is the favored models. That's why I didn't spend much time in describing the models. Face value, the best fit model is a Hernquist model, but you see the likelihood, the weighted average of all models is shown by this red line, and the uncertainties here is in the orange contour. And in the end, you know, so the best fit Navarro-Franke-White is a good model. So it looks like we are a bit less concentrated mass than Navarro-Franke-White, but this is not really significant at all. Okay, so now once you have all this this mass profile model, you can also compute which is the likelihood, the weighted average concentration that you get from running MAMPOS with all these models. Some models will have higher likelihood, like Hernquist. Some will have a lower one. And in the end, you can weight by these likelihoods all the models and get the concentration. And the concentration in this case is not the concentration of a spatial distribution of galaxies. This is concentration of the mass. Okay, so in MAMPOS, number density and mass density are fitted separately. Okay, so we don't assume the light follows mass. So this is the result in the concentration versus redshift plane, where I'm putting together the data from the literature. All these diamonds indicate the error bars for determination from the literature on the vertical axis, and the range in redshift of the sample which is being considered in the literature reference. And you see that more or less these points gathered around here, they are more or less consistent with the two models which are shown here, Bhattacharya and the Boni. The low redshift one is more consistent with the Boni. And certainly our G-class result of 4 years ago was indicating some tension with the models, but especially with the Bhattacharya model. And now our new result is here, the square, and the tension is even stronger, and it basically confirms the, sorry, the previous result. Now, if you split our sample in G-class and go green, where G-class is also the go green data now. So these are all the clusters which were originally in G-class plus the data from go green. So it actually sits, the points should sit at the same redshift here, but I just displayed that for the sake of visualization. You see that we confirm the G-class result with smaller error bars. We now get a point, a higher redshift, 1.25 on average here from go green, which confirms the fact that basically it seems like concentration is evolution. There's no evolution at all in concentration. And it starts to be significantly at odds with the prediction from the simulation. Although this point here is from a lensing analysis, and it seems to be also at odds with our determination. So there is some tension with theory, some tension with the other observation, which of course it's interesting. Let me go to the last 3 minutes of velocity isotope profile. So basically, using the mass profile from MAMPOS, we derive this velocity isotope profile, which is, I'm indicating not beta, but the ratio between the radial velocity dispersion and tangential velocity dispersion. And as you can see, well, isotropic orbits would have this ratio equal 1, radial orbits ratio greater than 1, tangential orbits ratio less than 1. So you see there is increasing radial anisotropy with increasing distance from the cluster center. Okay, and this was the old G-class result 4 years ago. You can see here that the error bars have significantly narrowed. The result is fully consistent, but at least now we can definitely reject isotropic orbits for these galaxies outside the center. It also compares very well with this result from Munari, my former student, based on numerical simulation. You look at here at basically the same redshift as the current sample, and putting these two together, you see that the curve is very similar. It goes from 1 to 1.2 2 basically, which is also what we have here, from 1 to 1.2 more or less. So it's a very good agreement with simulations. What simulations predict is also that low mass clusters and high mass clusters has a slightly different velocity and isotope profile, which we also do find here when we split the sample in high M200 and low M200 clusters. Although, of course, the error bars are now large enough that it's not significantly different. But at least we see the same trend. High mass clusters have more radial isotopy. And then the prediction from Munari is also that when you go from high redshift to low redshift clusters, the velocity isotropy would decrease a bit. And for that, we can compare with the results from WINGS, Mamon, Kava, myself, and all the WINGS people, which are shown dashed line here. And you do see that if we split them on star-forming and quiescent galaxies, we do see some difference in our sample, but not a large radii. These are the solid lines. While WINGS do see a difference at all radii between quiescent galaxies, E and S0s, and spirals in blue. In fact, the low redshift spirals have a similar velocity isotope profile to our star-forming galaxies, more than the quiescent galaxies do with respect to the elliptical S0 or low redshift. So there seems to be some evolution of the orbits for quiescent galaxies. Again, this is, very 1 sigma result. So, but face value, we do confirm this trend of isotopization of orbits in the seen in numerical simulation. And finally, for the orbits, although we do see some difference between the solid blue line and solid red line here, quiescent star forming, the difference is much stronger when you divide the sample in low stellar mass galaxies and high stellar mass galaxies. The thin line, low stellar mass, and the thick line, high stellar mass. Again, the error bars are large, so it's not significant, but seems to indicate that isotropization of orbits is more related to the stellar mass than to the star formation of the galaxy. So I'm here the summary. I'm 1 minute late, sorry. The mass profile is the highest redshift cluster mass profile determination so far. Unfortunately, statistics is not yet good enough to discriminate among different mass profile models. But we do find the mass concentration is significantly higher than predicted from simulation. It's more in agreement with the hydro simulation of the Boni than with the dark matter-only simulation of Bhattacharya. So this is a hint that perhaps what's lacking in the simulation to reproduce our result is that the baryonic physics is not fully accounted in the simulation. It's at least partly accounted in the Boni simulation. And the second and last slide here is about the velocity isotopy profile, the orbits. Again, it's the highest redshift cluster orbits determination so far. We find that the orbits change from slightly tangential near center to slightly radial outside. And although the other 3 conclusions are lacking significant statistical evidence, I provide them here. There seems to be more radial orbits for galaxies in more massive clusters. There seems to be moderate evolution with redshift, becoming more isotropic orbits at low redshift. And galaxies of lower stellar mass seems to be on more radial orbits. And the results 2 to 4 is appear in agreement with prediction from numerical simulation. And I stop here. Thank you.
Thank you, Andrea. It's great. So again, I'm willing to let the schedule slip a little bit into our discussion period. If there's a quick question now, we can take it. Otherwise, add your questions in the chat and we'll come back later. Any quick question for Andrea?
There's a question in the chat.
Yeah, it's not, so Mike Hudson noticed that the WINGS isotropic orbits look more isotropic than the simulations at redshift 0.
Let me just see.
Didn't catch that myself.
The WINGS isotropic orbits look more isotropic than simulation. That's right. That's right. Yeah. I don't have an explanation for that. In fact, I would say that there are other simulations. I remember, for instance, Knutsen Dolag, and then the same team that did find conflicting results among themselves, so to say. What was the other name? Lots et al. Basically, some simulations indicate that red galaxies actually have more radial orbits than blue galaxies and vice versa, and that these radial orbits do not change with the redshift. So, yeah, I don't have an answer for that. My hint, which I hope I will have some time to explore in simulation. There's some indication of that in the simulation of the group of Borgani and people, is that when you know, radial orbits are something like a low entropy status, dynamically speaking, in the sense that you need some order in the cluster to have the radial orbits. When the cluster you have a collision, you expect that this entropy, dynamical entropy, is enhanced, and this would destroy the radial orbit's regular inflow. And so you will get this kind of isotopization. So this is my guess, is that apparently there's something which is, this could be the process, but I don't know why in simulation this is not.
I guess a follow-on question that's related. I don't know much about the simulations. How are these fully hydro simulations, or semi-analytic, or are they just pure n-body?
Lunar is fully hydro.
Galaxies, I guess, if they have different types, right? There must be some galaxy formation in them.
Maybe it's helpful because it's our simulations, so high. It's Miria, and it's full hydro, it's a full cosmological box, it's a magneticum simulation that you were talking about.
Yeah.
And normally all physics should be in. So why we find discrepancy, because you also work with the Borgani group, we don't know yet. So just clarify.
Great, thanks.
I would say that it might have to do with the survival of galaxies in the simulations. You know, all this issue about which, what's his name? Yeah, I don't remember. You know, that in the end, we're not certain the simulations are able to fully preserve the galaxies from total disruption when they approach the center. If that's the case, that would be an issue. I don't know.
Okay, thank you. We should move on.